All right, so we're going to look at the normal distribution. This chapter 5, it's big in the book. It's actually very few concepts in here, but the concepts get used for almost everything else we're going to do. And so you're going to find that we're going to talk about this a little bit before the first exam, talk about it a little bit after the first exam, and talk about it and talk about it and talk about it. A standard normal distribution is, most people know it. Whoops, I keep doing that. I'm sorry about that. Really don't want to restart this, so I'll just come over here. So we look at, well, the standard normal distribution, standard normal, Gaussian, and the bell curve are what they tend to be known by. And they have a particular shape. And I'm doing this freehand, but you should look at the pictures in the book to help you with it. And they are continuous. There is no individual thing. There is a collection of things. And there's so many things that they fill this space. But at least that's how we're going to look at this. And so if I'm measuring 1, 2, 3, 4, 5, 6, 7, 8, and so on, there's a chance I can get 2.149. There's a chance I can get 5.487. I'm not counting up how many things fall into a particular place. I'm getting a particular value. And so now we can talk about, what's the probability of, I cut this and it's going to be 6.3 inches, right? Cut it another time, I get 6.28. Cut it another time, I get 6.31. What is the probability of something that's measured continuously, not discretely? And the idea and why this is used so much is we have to think reality has some true value, right? And I talked about this before, but I'll keep coming back to this, right? The thing has a real value, and if I manufacture it, there's a little bit of error. But if the error is completely random, each error can come about in some small little error. Sometimes I get values on either side of the true value. And it should be rare for me to get a large error. And that's what this shape shows. This shows that the true value is going to be the mean, and it's going to come right down the middle. And this is going to be symmetric, not from my drawing, but it's going to be symmetric. And just like we saw in descriptive statistics, this shape determines kind of where percentages of stuff fall. And with things being very small and rare and unusual far away. In fact, we're going to be able to use z-scores as a way of navigating our normal distribution. So let's talk about this in detail and programmatically. And so what we have is a continuous variable, and so in this case, again, I'm going to follow the slides distribution, distribution example, and look at the hours spent studying in a day. Well, there is a discrete number of hours in a day. There's exactly 24. We have 0 to 24. But this is a closed interval on the real number line. I can get the endpoint. I can have exactly 0. Hopefully we don't have a 0 studying in a day. You should study a little bit each day. I can get exactly 24. Hope you don't do that either. There needs to be other stuff in the middle. Or I can, more realistically, I spend 2.4 hours studying. And other values that are continuous. And so the probability that we're looking at is that is a variable that is continuous. And so the normal distribution is one of many continuous probability distributions, but it's one of the more important. We'll look at t distributions later and f distributions, but the normal distribution. And in fact, the way we use the word normal is actually influenced by this distribution. There's some weird etymology between the history of the word and the mathematics. The concept we have of normal probably didn't exist before we mathematically started talking about it in the 1800s. People didn't really talk about custom normals, and they didn't have the language for it, even though it was a recognized thing. There were traditions and standards and whatnot, but normal became a way of measuring things. There's not all good with this. There's a lot of problems with some of the early literature on this, and especially when it was being applied to social things. But from a scientific standpoint, it has a way of looking at the truth. And one of our challenges is going to be to read it in a way that minimizes the bias and not to abuse the use of it. And we will develop those skills, right? I will say that the history of normal distributions bugs me too. And a lot of times what we find is that we're measuring the things we choose to measure is actually what it's telling us. Not that that's bad, but then why did we choose to measure those things? And then what do we do with that information? Alright, so this is the distribution, and it has a middle. Now, I will try to refer to this curve as the Gaussian. Gauss was the mathematician who put the mathematical formulation on the Gaussian. We won't deal with it in a pure mathematical sense. We'll deal with it where we will have computational methods work out answers for us. And so the mean is in the middle. And so for a normal distribution, the mean, the median, and the mode are all equal. So it's symmetric about the middle, and they all define the same point as the middle. If we can think about being a collection of stuff, think about making a lot of histograms, loads and loads and loads and loads and loads of histograms, and then we get this, right? There's many, many small histograms in the bins, there's so many of them, and it's shaped like this. And I've been pointing out that shape that we see it in histograms occasionally. And so the most stuff is in this column that follows right down the middle. And so that's why the mode's there. And it's symmetric about the mean, and it has a bell shape. And if I've made my probability where the probability of success is 1, then in the area under the curve, if I were to paint this curve, the area under the curve is 1. Right? To have a probability distribution, it has to add up to 1. That was one of the things we did when making probability distributions. And so if a section up above represents the kind of probability, the number of things, or the frequency that we would see at any given value, then in the area underneath here has to equal 1. The chance of me getting a value underneath this is 100%, is what that says. Well, what that means is when we go to find probabilities, we have to find them between 2 points. And we'll talk about this being a delta, right? Some difference between two x values. And we'll talk about the probability of finding a range of values. And that's one of the problems with continuous variables. In statistics, it's often called the dartboard problem, right? If I have a dartboard, right, and I can imagine it being mathematically infinite amount of points on it, right? I could be the point here, or I could be some point to the side of it, right? I can always create a new point, and so there's an infinite number of points. If I throw a dart that's the size of a point, right, infinitely small, my chances of hitting a point are impossible. Any given point, my chance of hitting it is impossible. Statistically impossible. I mean, this is one of the things in the foundations. Like when you take graduate level statistics courses, they have you, use these to build all the rules of mathematics. And this is one of the fundamental things we have to do when looking at these continuous things is, I've got an infinite possible number of values. How do I figure it out? But a real live dart has a small size to it. And so the chance of hitting a space is based off of the size of the space. And you look at a real dartboard, and it has the big circle and the little circle, and you get more points for the smaller the area is because it's statistically harder to hit. And that harder to hit it goes with the probability. It's the size. The smaller it is, the less chance you have of getting it. The larger it is, the more you have to get it. And so the area under the curve and the area in our regions turn into our probabilities. Now, mathematically, this goes off to infinity. It never gets to zero. Realistically, we have places where we say it's so close to zero, we're going to call it zero. But the math that we create, because these points are infinitely small, I have to have an infinite length to this curve. And so the mathematical tool we use isn't really, it's realistic, but we have to realize that these arms go off to infinity and they never get to zero. But if we're far enough down over here somewhere, we're like, well, it's close to 0% of the stuff is there. And it's just some mathematical dances that we have to work with. If we use standard deviations as the means of measuring away from the mean, so the mean plus a standard deviation and the mean minus a standard deviation, then we have a way of talking about areas. And remember, in descriptive statistics, so plus 2 standard deviations and minus 2 standard deviations, and so on to 3 standard deviations, and so on. We have ways of talking about where certain percentages can fall. But at 1 standard deviation away, the curve changes shape. So in general, it's curving down. And then once it gets here, it starts curving up. And so over here, this is an upward shaped curve. And over on this side, it's a downward shaped curve. And that causes the speed at which it gets bigger to change. And so this is called an inflection point. And the inflection points are at 1 standard deviation. And that's why the standard deviations are important things to measure. Now, we can graph these with any probability, not the normal distribution, but any discrete probability distribution gets what's called a PDF, a probability distribution function. So our old friend, the discrete probability distribution, gets a probability density function. Sorry, probability density. I always say probability distribution function. It's probability density function. And for density, density tells you how much stuff is in a given space. So if we take the word from its terms in matter, if I have a lot of matter in something, it's more dense, it's heavier, right? Gold is more dense than water. There are more atoms in matter in gold than there is in the same volume of water. And so if I take a discrete probability distribution, I can look at its probability density function, and I can talk about how much stuff is in a given area. And so for the discrete case, we do this with histograms. That's what histograms have been doing for us. They've been telling us where the most stuff is. The little bins tell us how much stuff is in the bar that comes above it. And it has 2 requirements. The total area under the curve is 1, right? And we had that 1 creating probability distributions. They needed to add up to 1. And the probability density function can never be negative. Can't be negative. Can be 0. There can be things that have probability of 0, but we can't have less than 0. Right? Robert Downey Jr. will not let us do that. He's done with it. And so what we want to do is we want to look at how means and standard deviations kind of influence what happens. And so if I'm gonna, again, I'm gonna tend to use the sample in the slides. You can look at the slide. We're gonna look at things that have the same mean. And so I'm just gonna make the mean at like 3.5. I'm gonna make the mean for 3 different distribution functions, or for, probability density functions of different data. But what we're going to say is the standard deviation, how much the stuff deviates from the mean, is going to be different for each of them, so that we can get a sense of where the stuff is. Remember, the standard deviation is a measure of where the stuff is, how far it is away from the mean, how far does it deviate from the mean if we use the words. And what I'm going to do, let's see here, whoops. So if, and so what this tells me, again, I'm just going to draw the graph generally. Is that's a 1.5 from the mean of 3.5. Now this one is going to be steeper. And 2 things happen with this. And so that's a 0.7 and a 0.7. And so the inflection points get closer together. So with smaller standard deviations, the inflection points get closer together, and the amount of stuff in the mean gets larger, and so it gets higher, and your chances is higher than this space, right? And so 4.0, these inflection points get larger, and I want to try to make go, like a saucer. It's fairly flat, and that's your 4.0 standard deviation. And so the larger the standard deviation is, the more the things deviate from the mean, the more stuff there is running left to right, and the less the peak is. The smaller the standard deviation, it gets narrower, and most of the stuff is around the mean, which means it has to get taller. And so that's how the means and standard deviations work with the normal curves. And so just looking at a curve, we had graph data, I could say, hey, this one has the larger mean, right? I'll make mean 2 and mean 1. You can say mean 1 is bigger than mean 2 because it's to the right. This center, this symmetric center, is in the larger area of numbers. And we can say the standard deviation for number 2 and the standard deviation for number 1. We can definitely say the standard deviation for number 2 is greater than the standard deviation for number 1 because this is wider. And so visually, that's what these things we've been measuring means. And if we go back to descriptive statistics, if you remember some of those histograms you were doing, we're starting to see a sense of that shape was coming out. And we had means and standard deviations for these things. And so we can now kind of talk about, what we expect to see when we're getting data, especially if it follows the rules of normal distributions. All right. What we're going to do is I'm going to pause this lecture and I'm going to continue diving into section 1 on normal distributions. I'm going to clean up the screen and just save this in chunks.